Well, thank you for giving me this unconference slot. And if someone has any ideas on how to talk about something else, please do. I'm going to talk about visualization of machine learning of units of measure using PyViz. Actually, it's not PyViz, it's HoloViz. They recently changed the name to differentiate some of the things that they are doing. HoloViz is a subset of PyViz, but it's still okay to say that I'm using PyViz. However, I'm more interested in talking about the project itself that I'm visualizing. I already gave a lightning talk about what I'm doing with PyViz, and I'm going to repeat some of the things here, but I'm more interested in explaining what I'm doing with the units of measure. Think about it. Unit of measure is something that everyone is used to seeing in high school even, like you write a physics equation or any other equation, you always have to put in the units of measure, any number that you see. Well, people still do it, however, there's a big problem, and I'm going to show it in a minute or two. The problem started because I developed disease models. I'm a computational disease modeler, and I developed a diabetes model, and this diabetes model takes a lot of information in it from multiple sources. One of the sources it's taking into is data on clinical trials. Those clinical trials are now regulated, and by law, you have to report them. There's a US law, FDA law, that requires reporting of those clinical trials. Currently, or each time you check on ClinicalTrials.Gov, which is the registry that collects all the data, each time you check there, you'll find out that there are more and more clinical trials, currently over 300,000, but the number keeps on growing. Every few months it grows in much larger, much bigger, but it actually changes daily. In April, however, if you look only at the clinical trials with results, meaning with numerical data that is interesting for models, there were roughly 36,000 clinical trials with results, meaning with numbers. Each clinical trial has multiple numbers for demographics, statistics about demographics, and for representing outcomes, how many people died, how many had the heart attacks, and so on and so forth. And what was the average blood pressure, things like that. However, if you looked at all of those 36,000 clinical trials with results, you find that there are over 24,000 different units of measure reported, highly non-standardized. And the reason is because those were written textually. And humans make mistakes. Also, they copy-paste from the paper. All sorts of anomalies, Unicode characters. You will see some of those in a few minutes. So what I'm trying to do, I'm trying to get computers to understand actual medical data. And I've been doing this for over a decade now. To get to the point that computers understand medical data, they will have to understand the numbers in some points. Otherwise, it's like, oh, understand only the text? Do any NLP? No, you have to understand the numbers to run some numerical models or statistical models. So what I did is I collected information from existing unit standards, and there are a few, and I'm trying to do some machine learning that will help map all of those units that are non-standardized to the proper standards and also merge those standards. I'm going to show you later. And currently I allocated multiple standards. I'm going to show you a little bit about this later. But again, what I'm trying to do is I'm trying to make machines understand medical data. How much time it will take? So let's look at other things that happened in the past that were automated away, or not away, but at least to the point that a human now has problems competing. If you look at chess, in 1951, Turing created Champ, which is the first chess-playing program. Well, it's not the full chess, but it started. 1997, Deep Blue wins against world champion. This was Kasparov at the time. And you can see all of the evolution in between. And if you click on this, actually, and this is a PyViz option, since I'm using Markdown, I can include HTML. I can click on this. I'll get the Wikipedia page. I won't do this now because I want to talk about, actually, I did look at that. Anyway, back to my presentation. So this is what happened with computer chess. Let's look at driverless cars. We still don't see them in the streets. However, Waymo commercialized last year. Waymo is the Google driverless cars, basically. And after driving 10 million miles autonomously. I don't think I'm going to drive 10 million miles in my lifetime. But this is the achievement made 40 years approximately after they started experimenting with a car that stays between two lanes. So this is approximately the amount of time that takes for computers to solve difficult problems. The problem of solving medicine, like impersonating a doctor for a computer, will be much, much tougher because there's much more problems, many more problems with data, and also the problems with standardization. Chess was basically solved by algorithms and computing power. You can argue against it, but basically this is the solution. For driverless cars, you needed some machine learning and data and sensors as well. Yes, you will need sensors for medicine as well. We'll have to wear some of those. But eventually, if the data that we get is standardized and there's enough of it, I believe we can get to the point that we're close enough so a computer will act at least as good as a human, or by the fact that we can replicate computers easily, at least solve the problem of scarcity of doctors. Because those have to be trained for many years and then maintain their knowledge. And this problem, if you can do this automatically and then replicate it, will solve a lot of resources. But for this, there are a lot of work to do. And I wrote down several models that I thought that were important throughout time. And I don't know how much longer it's going to be you need to solve it. But when I ask experts, they tell me, I think one said 25 years and then 5 more years for policy to follow after that. But I think this is the furthest time I got from other experts. Maybe it will take us more. Maybe some of the problems will be solved before, but this is at the horizon. But to get there, we need to get computers to start walking before they start running. And they need to understand the numbers. They have to understand things that doctors today understand. And this is what I'm trying to solve, this one little step. And the solution that I currently have is I went to ClinicalTrials.Gov, downloaded data, batched it, indexed it. I got all the unique units. From later on, I extracted free standards from CDISC. CDISC actually is here in Austin. It's a place, their headquarters, or what was here in Austin. It's a standardization organization for healthcare, which is global. They are actually an open source standard. RTMMS is actually a project by NIST and IEEE. They also have a different standard for medical devices. And there's a website called Bioportal that has unit ontology inside it. So those free unit standards are the base, but also within RTMMS and CDISC, there's something called UCUM, which is also the unified code for units of measure, which is actually also kind of a unit standard. It's mostly how to combine units. So notice, in healthcare, you have 4 unit standards currently. Some of them repeat each other, and this partially explains some of the problem. Every person who put in information, or every entity who put in information in ClinicalTrials.Gov uses a different standard, and therefore all the problem. It's a Tower of Babel problem. So I extracted information for all those standards and actually merged it to the level that some of the units I can tell you, oh, they're the same across the board, and there are also synonyms for some of them. So I actually have a table of synonyms between standards. And now I'm trying to create some machine learning that if tomorrow you come up with a unit, I want the machine learning to be able to tell you which unit you actually meant. And I started by doing the following things. I started by looking at natural language processing. And later on, I did some machine learning and clustered it. Later on, I'm going to talk about supervised machine learning as well. But what I'm showing you now is unsupervised machine learning. The first thing I did is I took the units themselves, and for example, the unit participants with a big P and participants with a small p. This is a common thing that happens a lot. People just misspell different caps. You can see that they are, according to lexical proximity, they are very close to each other. It's a proximity of 1. However, participants in years, well, they are not the same, proximity of 0. So I'm showing this heat map here, and notice how nicely I can go around the cells here and show you exactly what I'm looking at. This is HoloView's capabilities. HoloView's sits on top of bokeh in this situation and allows you to do this nice heat map and allow you to have this interaction in this presentation. And this presentation is, in fact, a web page. So I can show it. But I showed it only to 30 units or something like this. I show you the proximity. I want the units to be ordered such that all the units that are the same to be close to each other. Why? For labeling purposes. I'm going to show it to you later. I want all the percentages to be near each other, all the participants to be near each other, things that look similar to be near each other. To do this, I need to order it. I'm showing you only 30 units. There are 25,000. You cannot even imagine 25,000, even how many pages. This is how this matrix looks like when you actually use data shader, HoloViews, together. And they create this huge matrix. And now you can see the diagonal is 1, because the unit always resembles itself. But then you can see all of the other resemblances. And data shader was able to compress it so I can actually show it to you. And you can explore this matrix again to see what the values are, although the values mean less now. Because some of the units, you cannot even, 1 pixel here represents multiple units. Think about it this way. So, but we want we want to cluster the units so they'll be close to each other. And indeed, I did this. I used k-means, and I did some tricks there. There are several publications at the end that explain what I did. I did it multiple times, and eventually I got to the point that I got a better representation. And let me show you how better it is. Look at this matrix for now, and I'm going to switch. I'm going to go back, unclustered, clustered. Which matrix seems better to you? I hope that you say the second one. But this one looks better to me. And notice the first one looks dark. The dark means that there's a lot of units that when I sum up and create this matrix, I sum up units that are close to each other and show the maximum. So if it's dark, this means that some unit is better than others there in that vicinity. But when it's generally lighter and there are only the dark areas here near the diagonal and it's thicker, this means it's much, much better clustered. Also, I have some other clustering methods, some other metrics to show you how I clustered it. And the one below shows you after clustering the number of the cluster. So before clustering, you'd see it's kind of not the same. After clustering, you see it's smooth. So this is what clustering did, and it did to this matrix. And now I'm going to show it to you because we created a website. The work I'm showing here is not only my own. It's with Josh Schertz. You can find his contact, his details here. We're both work independently, but we teamed up for that project. He created the website. Then the website actually allows us to use all of those units that we now cluster together and allow people to map them, meaning manually label them. The term is labeling, but if you tell the word labeling to people from the medical industry, they will think about the labels on the prescriptions drugs you're getting. So I'm using the word mapping here for a reason. So what you see here is the units clustered already. I'm showing only 3 clusters in this website. We have about 100 of those clusters. Each one of them represents sets of units that approximately resemble each other lexically. It doesn't mean that they are the same, but lexically they look the same. So if I switch between those, you will see things switch. So the first cluster is like things related to percent of something. Basically, all of those should be mapped to percent manually. A user can say, I want it to be mapped to percent, and you can see we started doing those. If you look at units of measure that are more complicated, then you can see those are usually associated with numbers that are not percents. You will see the unit. Now I'm showing the unit with escape characters and with, as it shows as Unicode. Why? Because sometimes some Unicode characters a user will not understand that they are not the same, and we want to do the mapping properly. And there are some Unicode issues, as you can see, like here's a Unicode issue. So we show the unit with escape characters with Unicode. We show how many times it is used in ClinicalTrials.Gov. We show suggestions by the system for alternative units that look close. Again, this is unsupervised learning. The system doesn't know anything about units. However, notice already we can mark those units that belong to existing standards. UCUM is a standard, CDISC is a standard, and if I scroll down or up, I'll probably find more units, maybe not in this situation, but some of those units will have, here, you see UCUM, RTMMS, and CDISC. This unit appears in all of those. It may not be the correct mapping, but the system tries as best as possible without human interventions to figure out what's happening. And to suggest this for the actual mapper. Because think about it, someone who's going to map 25,000 units, or even if it is a group of people, we don't want the user number 1 looking at unit number 1, encountering that same unit 2,000 times later and thinking, oh yes, it's something new, and map it to something else. We want all the mappings to be concise, so we want to put all the mappings together. So unsupervised learning helps us do this. The system will also show us the clinical trials the unit is associated with. So in case there are multiple clinical trials, you will see all the clinical trials. And the system allows you, the person, to actually press on the web button, and there's a web button here that will allow the user to see actually the clinical trial. So this is the mapping website. This is designed for labeling. After we have the labeling, what happens? Well, once we do the labeling, we want the machine to be able to learn in a supervised manner actually what the units are. So if someone makes a mistake in the future that the character is incorrect, or adds a character or removes a character, the system will tell, oh, you probably meant that. Think about it as a spell checker, as a glorified spell checker for units. So to do this, we started supervised machine learning. I will not go much into details here, but we tried multiple architectures, and using PyViz, it allows us to create this nice table, and those links are hyperlinks. If I click on it, you'll actually see what architectures we tried to implement. And from those architectures, we chose mostly architectures that deal with LSTM and CNN layers, feed-forward neural networks, basically. But there are other architectures we tried learning to rank, all sorts of variations on encoding with embedded, with one hot. And notice, we also, with the units, we also have the unit context. You've seen it before at the clinical trial. It actually shows the context of a unit. So for example, percent, actually I'll show you. This unit is associated with maximum concentration. So this is another source of information that we can ingest into the system to actually try to help the system figure out what the unit is. Not only what is written, but also what is the context. So we also tried multiple unit. We also tried adding inputs, sometimes only the unit, sometimes the context, and sometimes both. And all of this is written in one architecture that we can change and morph. There's one program that allows us to morph between the architectures. Now, I must say the problem here is kind of tough because we haven't done the mapping yet. We just prepared everything for the mapping. The mapping is the next stage we're going to do, and this happens before supervised learning, but we already have the supervised learning program. And how do we do it? We use the clustering data that suggests what is the best unit and learns the best unit that the clustering method suggests for each one of the units. So it's not ideal, but it's something to start and develop the neural networks and figure out which one works better, because the mapping process takes effort and money, or time, while it's easier to code the neural networks, especially with the tools that we have today. We used Keras, or actually TensorFlow 2.0, but we went through multiple versions of TensorFlow to get where we are. I'm going to show you some results, and I'm going to show you some of the different architectures that we tried, and you can see each one of those has some results. On top, you can see the training, how good the training was, and you can see it for encoded, decoder, basically sequence-to-sequence neural network, multiple LSTM layers, LSTM and CNN combined, and CNN layers only. All of those we can do, and we can compare the results, and you can see how accurate it is immediately. Whatever the systems now, they actually translate a sequence of characters to a sequence of characters. And later on, when you add additional information about things you know about the units, you can now get a better prediction. The training data, it's easy. It's basically the units kind of got memorized by the neural network. Let's look at the validation. The best network we got to is LSTM networks. And we had several metrics to figure out how accurate we are. And I won't go into details here, but I'll just go back to this graph over here and say, when we combine the multiple metrics of how accurate we are, and those metrics include other things on top of the neural network, we can see that if we use only on the validation data set, now I'm talking, this is basically the accuracy of the neural network. If we use only the unit, we're about 56% accurate. So more than 50% of the time, you give us a misspelled unit, we'll be able to give you the correct unit immediately. However, if you give it multiple tries, up until 10 tries, you get to almost 80%, 78%. We believe those numbers can be made much, much better, but this is what we start with. And again, we haven't done the labeling yet. And notice that we tried it to see whether it's better when we add unit on context or when we look at context only. If we looked and tried to figure out the units only by context, ignoring what the unit, the misspelled unit is, then accuracy is not very good. So 60% of the time it's accurate. And it makes sense. Sometimes, like distance, you can measure with multiple things. You can measure in centimeters, meters, and so on and so forth. So there are reasons why the context is not necessarily accurate all the time. However, the interesting part is that when you use unit and context as input, we're not as accurate as we use only the unit alone. This is because we add additional information that kind of confuses the network. However, we still keep this option open, just in case we believe it will improve when we move forward. But these are like preliminary results we have now. We already have the neural networks. We just need to train them with the data after we did the mapping. We haven't done the mapping yet. Now, during the training process, I had problems in actually figuring out sometimes why is the neural network not doing what it's supposed to do. So I wanted to look inside the black box, inside the neural network, just to see how it trains and which layer trains better, which layers get better training than others. And many people outside the machine learning field say that neural network is a black box. You can't believe, you don't know what's happening inside. Well, I have news for those people. It's not a black box. You can see exactly what's happening during training. Yes, it's hard to understand, but with PyViz technology or HoloViz, actually here it's again data scheduler and HoloViz, you can actually see from the beginning of training, and I'm running for time, you can see the change in the weight of the neural unit. You can actually figure out what happened here. And you can do it, I'm showing one layer, but you can also look at the bias, and since it's an LSTM layer, you can look at the recurl kernel. You can look at all those and see how those change throughout time. This actually helped me find out and understand the problem in this that I had during training and helped me resolve it. So it's a good debug tool. And interestingly enough, it is not supported by TensorBoard, for example, that comes with TensorFlow. At least I don't know how to do this in TensorBoard. I'll be accurate in this. Again, the training process itself with HoloViz can be done much nicer than whatever Keras provides off the top. You can actually go and look at how accurate things are during training, and you get all those nice hover tools that you can go and see, and you can dismiss or not dismiss this or that graph. So at this point, I want to summarize and tell you that we have all the tools necessary to actually go ahead and do the project of unifying all those units of measure and solving that problem that I showed you. I must say that the people at ClinicalTrials.Gov, the government people who created it, did a great job. Before they had the website, it took weeks of actually taking one of those pieces of information that are in the literature and plugging it into code. Now it takes a few hours, partially because of issues like that, because of this Tower of Babel problem. You have to overcome all sorts of differences between different entities entering the data. So they already did great, but they're a small team that with many users, and I believe that tools like this from the open source community can help them move forward and help us move forward in actually making computers understand units. If computers understand units, they can understand the numbers. And I'm not talking only the numbers in ClinicalTrials.Gov. I won't tell you more, but think about it yourself. You can extend it easily to other things. And also, if we continue doing this and continue automating small little bits like this, eventually we'll get to the point that computers will automate away some of the reasoning tasks humans do. Think about it. Today, if you have a unit with a number, you have to ask the doctor. The doctor has to be trained for many years. It's a valuable resource, it's a scarce commodity. So it's like this, if you had computers automate this, problem will be solved. Or at least halfway. And I want to add that today I no longer do presentations with PowerPoints. It's all in one HTML page like this that's accessible using a QR code like this. And if you want additional information, even on reproducibility, and by the way, the code for this presentation is at GitHub. If you want more additional information or see who are contributed by helping or look at additional publications, you can just download them. Much better than having a document. So I think I've conveyed the ideas that what the project we're doing and how we're solving it using PyViz, or more specifically, HoloViz. I'm open for questions if you have some.
What are other countries doing? I mean, I work with medical records at the Veterans Administration, and we have a lot of the same problems, even with our own internal users in different parts of the country using different units of data. And I'm just curious to know what other folks all over the world are doing.
I'll try to repeat as best as I can the question. So you say that you're asking what other countries in the world are doing, and you're asking, and you're saying that you, from personal knowledge, are dealing with data similar to this, and you know the problems. Am I correct?
Yes, same challenges. Yeah.
Okay, same challenges. This is what your words were. Okay, so I can inform you happily. The U.S. is leading. U.S. is now the registry for ClinicalTrials.gov is the only country that by law collects this data, meaning many countries conduct clinical trials. They are all reported in ClinicalTrials.Gov. The clinical trials I was talking about before, they are contributed by multiple entities globally. I think, I don't remember the exact number, but if you click on some of the, if you go to ClinicalTrials.Gov, you'll figure out that exactly how many countries they actually show it. Actually, we should just try doing it. And you will see, they actually have it. This is for today.
What are people doing about the units problem, or
yeah.
about just getting access to
The unit problem.
So 209 countries. The unit problem, well, people currently are standardizing units in CDISC, and CDISC is one of the better standards out there, and CDISC is actually, I can tell you again, US is leading, because all of those CDISC units eventually get absorbed into something called UMLS, Unified Medical Language System. So part of the ideas of this project is actually contribute those AI tools and standardized units after we collected all of those back to the entire pipeline, so it will appear in those standards. But at the same time, have this safeguard machine learning that in case someone has a misspelling, the user will be guided to the correct unit. So US is leading from several aspects because people around the world are solving it using standardization, not using machine learning tools as I'm suggesting currently. But in any case, there are multiple standards. This is also part of the problem, as I showed, and it has to, those have to be merged. Did I answer your question?
You did, yes. Thank you.
Thank you.
I was just going to ask if you could just expand a bit more on your context. What context are you bringing in to the...
Exactly those words. It's text. So actually, the context, when you go to the neural network, there are so many words that it has to go through an embedding layer. So this is partially why a lot of information is lost, because a lot of the words appear like once or twice, even within the context that is provided in ClinicalTrials.Gov. You can extend it even further. Currently, I'm just looking at the unit and the associated exact
The
context.
number itself is not brought into the context?
Currently not. However, you brought in a good thing. The number itself represents things, and some things can be later done. I won't spend too much time on it, but you can think immediately. You can think easily what can be done once the numbers are there. But this is not yet. Look, this project is not that old, as you know. So the idea is to expand as much as possible. Currently, the next stage that is critical is actually doing the labeling. If anyone knows of ways of actually helping out and doing the labeling, please come talk to me. And if anyone sees this video and wants to help with the labeling, please do contact me. You can find my information by Googling my last name, or you can contact Josh, and we will help you out with this. Well, thank you.